Hello, 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 hello. Hello, hello,
Good afternoon, everyone. On behalf of Sri Venkateshwara College of Engineering, Tirupati, I extend a very warm welcome to all of you present here in our AICTE sponsored 1 week short term training program on research trends in renewable photovoltaic system and its research challenges phase 2. So I ensure the training will be more profitable. And now I feel much honored to welcome our Strength and Energy of Triply Department, Dr. Sudhir Kumar sir, Head of the Department. Welcome, sir. So before going to start the session, here are some instructions. Do follow them. So all the participants are requested to mute your microphones and turn off your cameras. And now all the participants are requested to pin the resource person screen and also suggested to listen the session and note down the key points and post your queries in the chat box. During query session, all the queries will be answered by the resource person. And now we are going to listen the presentation given by the resource person on challenges in renewable resource integration. So as I humbly introduce and welcome Dr. K. Palanisamy, presently working as Associate Professor in School of Electrical Engineering of VIT University and University Energy Audit Committee member. He has 6 years of teaching experience and has completed his BE at KSR College of Technology, Tiruchengood, and did ME at Coimbatore Institute of Technology and also completed his PhD in Power Quality Improvement at VIT University. He also published 51 international journals and attended 18 international conferences and 8 national conferences. Sir published 7 book chapters in reputed publications and edited 1 book. He is also a member of IEEE, IET, and SEEM. His areas of interest are low inertia microgrid, smart grid, power quality improvement, and electric machines and power electronics. So, a person of such magnitude truly inspires. His guidance and presence is a source of great motivation for us. So, now I request Dr. K. Palanisamy sir to take up this session. Welcome, sir.
Sir, good afternoon, sir. Palani, sir.
Good afternoon, Sudhir and others.
Sir, thank you so much, sir, being here in our AICTE STTP, sir.
Thank you.
Sir, I just want to convey 2 points, sir, before your session with your permission, sir.
Yeah, please.
Dear participants, sir has a very good experience in power electronics as well as in smart grids. So, sir is one of my favorite professor in VIT University, and he's one of the guru. I really assure you, sir will share valuable points to all of you. Please make use of this session. So, thank you so much, sir. So, please take over the session, sir.
Yeah, thank you very much. I hope my screen is visible to all.
Yes, sir, visible, sir.
Okay. Thank you for the nice introduction. Before starting into or getting into this topic, this is very wide. All of you can understand. See, when you say the integration issues or challenges of renewable energy integration, right? Let it be on grid or off grid, standalone system or grid connected system, whatever may be the case, there are certain challenges still under deep research, and many researchers are working on it to find the best solution possible. And also, it is an evergreen field actually. When we say RES integration, definitely we will very well be connected with smart grid, right? So in smart grid, it is not just electrical engineering alone. There are much more than that, right? So you can say information, that means the communication, IoT, then the best business model for a smart grid, to share the transmission line, to operate, right? A grid operator, right? The grid operator is not just an electrical engineer. He must be expert in the economics, energy economics, right? So everything. So when we say challenges the renewable energy sources, it involves many things, right? We should not give overburden to the grid operator, or transmission system operator, or distribution system operator, DSO, or as a smart grid whole. We should not create too much burden, right? It means, in a simple way, my gurus used to tell me, like, if you want to climb your microgrid, or your grid is very smart, right? It means right? It means your system must be a controllable entity, or you can say you must present to the main grid, the overall grid, as a controllable load or source, right? If grid asks, you must be in a position to change your power delivery, power, or you must be in a position to change the parameters, like including voltage, real reactive power, everything, right? So it means you must be a flexible, controllable entity to the grid, or otherwise I can say you must be a flexible load, in some cases. Okay, so that is where the challenges and other things comes into picture, right? First of all, when you interconnect more and more renewable sources, please listen it carefully. When you integrate or when you interconnect more and more renewables to the main grid, right? Yeah, microgrid or main grid, whatever it is, because in many of the developed countries, right, the electricity network is a combination of several interconnected microgrids, right? So between one microgrid to the other microgrid, there must be energy transaction, peer-to-peer energy transaction, based on the demand, based on the need. There must be a transaction between two microgrids, right? So that's something like a transactive energy based on the need, right? Based on your situation and your status, you must be in a position to interchange the energy, power, or whatever is on demand to the nearby microgrid, or to the entire grid, right? So that is how it is, it is going to be to hereafter. Okay, so when you say like that, it is not a conventional, synchronous generator based system. Just we are moving very fast away from the conventional grid, right, or setup. Okay, so what way, right? Why it is so? If you just expand it, or if you just go into deep, you can understand that when the grid, right, when the power system is mainly based on, or mainly on synchronous generator based power generation, then I can say there is no issue at all, right? Because the earlier grids are the sources are far away from the consumer, and the sources are very limited, very less in number, right? 1000 megawatt, 800 megawatt, 2000 megawatt, something like this, right? If you take super thermal power plants, it is all like 1500 megawatt, something like that, right? Those are very limited, and from there the power is maybe a few hundred kilometers away from the generation, right? Something like this. If you see, the source and load point or load centers are connected with a huge transmission line, and I hope right, which is flowing in the transmission line is huge, right? Or in the other term, I can say the inductance involved, reactance involved with the transmission line is enormous, right? So if at all there's a small change See, the small, in the sense, how small, it depends on the system which we are talking about, right? If you're talking about, 1,70,000 megawatt or few hundred gigawatt, then small in the sense like even few hundred megawatt is a small quantity, right? So in the grid, in the conventional grid, where the sources are mainly based on synchronous generator, if there's a small change, in the sense loss of few hundred to 1,000 megawatt or even few thousand megawatt, or addition of big generating station, or losing of a particular feeder, let us say a metropolitan city is disconnected from the main grid, or a big city of few thousand megawatt demand is disconnected from the city, a particular feeder, city, district, right, or state, it depends, right? If that is disconnected from the grid, or a big load is connected coming into the system, into the grid, then I can say it's a change, right? I can say it is a contingency, right? Contingency. Okay. So how it is managed, or it was managed in the past, since I told you the generation is one place, few hundred kilometers away from the load point or load center. So it was fully, a big inductance. It is, the inertia associated with the inductance, high reactance, right? Will itself can handle, a small changes. That is one thing. Or a big rotating mass, which is associated with the synchronous generator, that is your rotor, right? Of several generators, right? Let us say hundreds of generators are connected to the main grid. Frequency will not change at all, because a big mass which is rotating at very high speed, right? 1,500 or 1,400 meters RPM, revolution per minute, right? It is having lot of huge kinetic energy, right? When there's a small change in load or generation, loss of generation or addition of load, or addition of generation or loss of load, it is reverse. Okay. So when there's a small change, the big rotating mass, a huge rotating mass, which is associated directly with the synchronous generator, will take care, right? The kinetic energy stored in the rotor for a time being, it will start to supply the energy. So what will happen? So the frequency will not change, the rate of change of frequency, or for a moment, for a time being, right? The energy will be supplied from the kinetic energy of the rotating mass, right? This was the case, right? Now what we are doing, we are slowly moving towards the power converters, power electronic converter based power system. That is our present microgrid, right? See, I can tell you one, very important figure. Even this, 2020 September, October, right? In fact, even July also, right? July, August, September, October, especially September. Okay. This year, last year September, last year September, I can tell you one, statistic. See, Tamil Nadu is having the maximum demand of somewhere around 13,500 megawatt. Somewhere around 13,500 megawatt maximum demand, and average demand of around 10,000 megawatt. An average demand of around 10,000 megawatt. Okay. See, out of this 10,000 megawatt average demand, somewhere around 7,000 to 7,500 megawatt is supplied by the wind generation, windmills. You can imagine. See, out of 10,000 megawatt of demand, average demand, 70 to so you can imagine, we have just like that exceeded 70% of renewables to the grid, especially Tamil Nadu, let us say, right? Tamil Nadu systems. Okay. See, you must understand one very important thing. The developed countries, so-called, that is, Denmark and other, electricity boards or electricity systems. Okay. They are talking about, even now, they are talking about, okay, when the renewable exceeds 50%, how are we going to manage? But see, in Tamil Nadu, of course, in many states of the India, right? We have just like that crossed or exceeded more than 50%, just like it's 75% of the demand is met by the renewable energy sources, especially wind, right? And in the wind also, you must understand, see, the conventional, or you can say around 20, 15 years back, the generators were induction generators. Then slowly, DFIG, then, PMSM based, and now the full, full power rated converter based windmills. It means when you say 2 megawatt of windmill, one particular windmill, the entire 2 megawatt, right? The mechanical system is just like the decoupled. It means the 2 megawatt variable frequency, variable voltage, variable cell, whatever you say, everything is variable. That is connected to the converter in the front end. Then it is rectified. Then it is inverted based on the need. It will be synchronized, synced to the grid. So it is full rated power converter based windmills. Okay. Not only this 2 megawatt, most of the cases, like even it started from 680, 1 megawatt, even now it is 8 megawatt. So everything is having, you are decoupling the mechanical rotating mass from the grid. So you are, isolating the, or you are just going away from the inertia. The, inherent inertial response of the windmill is just decoupled, is just disconnected. So what will happen? Because of this more and more renewable, penetration, when there's a small loss of a generating unit or addition of some load, a big load, right? A particular region of load is suddenly connected to the grid. What will happen? Immediately, because of the lack of inertia, the rate of change of frequency operator to manage, to handle, right? But in earlier system, that means like 15-20 years back, the system was full of synchronous generator. When there's a small addition or small loss of generating unit, the kinetic energy stored in the rotor, big mass, right, will be released for time being. Then immediately after that, your primary and secondary frequency control will come into picture. Then you will have a improved response. Right. So the frequency will be recovered or restored to the actual value within few minutes, right? And in the intermediate or the in between time, it means the transient, right, will be taken care by the inertia, rotating mass of the big synchronous generator, right? So I hope you can understand. See, I was or I am trying to connect two things. One is when there's a conventional synchronous generator and the transmission was inductance, it means the transmission line, right? Also, the inertia associated with the synchronous generator will be taking care of the change of frequency. For time being, it will supply. Immediately after some time, the frequency control will comes into picture. So you can, you can do some actuation or you can release some actuator so that, the excess fuel or, whatever, right, is required, that will be taken care. Or the spinning reserve, which are running at a light load or even no load, will take care of the frequency restoration or the recovery of frequency. But nowadays, if there's a small loss, right, immediately the system frequency will go to the very low extent, right? Maybe if it is a 50 Hz system, even it may go to 48 Hz also. But it was not the case in the earlier power system. Okay. So these are the issues, right? It directly affects the security of the power system, right? Now, we'll come to the other part of the security issue. Let us say our grid operator is, very intelligent and is having or is planning to have more and more spinning reserve, right? Or some kind of reserve. Okay, right. So what will happen when there's a sudden change in power? Let us say few hundred to few thousand megawatt. We are not sure about the spinning reserve, how effective in handling this ramp. I'm just using the word ramp in the sense how fast a source can handle the addition of excess active power requirement, or how fast a generator can reduce its power generation, right? How fast it can take up the increase load, few hundred to few thousand megawatt, or how fast it can decrease from an earlier generation of, let us say, few thousand megawatt to a lower value. So we are not sure about how effectively that can be handled by the spinning reserve. are the kind of source which we are thinking of will support during the contingency, right? See, if it is a battery kind of things or any kind of energy storage, yes, to some extent it will support. But if it is a generator of 20 years old or 15 years old, that retrofitting, the kind of retrofitting involved or associated with that older power plant may not support to the high ramp. Positive or negative RAM cannot be supported by the older power plant. It is very difficult. Why I am talking about older power plant? Because when you say spinning reserve, the highly efficient power plants will be taking care of the entire load, base load, let us say, right? But the power plants which are not considered up to the mark, right? It means the efficiency is not up to the mark. Then we used to consider that as a reserve. So we will run light load or no load, and whenever there is a need, then we will take a we will consider that to match to balance the demand, right? So these are the issues, right? And all these sessions or all these discussions are going to take care of that one only. Okay. See, the challenges are enormous, but I'm going to address or deal very few issues, very few challenges. Okay, right? As I told you, the main challenge comes from the displacement of conventional synchronous generator by a power electronic converter based RES, whether it is a solar PV or wind or whatever the renewable energy sources you consider. It is all power electronic based mostly, right? So induction generators are very less in quantity as well as the overall rating. Okay. Now you try to understand. See, I told you the inertia, right? Kinetic energy and inertia, right? See, the kinetic energy E equal to half J omega squared. So kinetic energy I told it is E, right? So it is megawatt into seconds, right? Because of this only, when there's a change, immediately the kinetic energy stored in the the system or the big rotating mass will come into picture, right? So J is the moment of inertia, it is related to the system, and omega is the angular velocity of the rotor. Higher the rotor speed, yes, you can have higher the kinetic energy. That's what I feel, the flywheel, right? The recent years, many of the energy storage engineers, right? Many of the energy storage engineers are talking about the flywheel, right? Normally or mostly flywheels are kept in the vacuum things, and the very light material which can handle at very high energy, right? So reinforced the rubber kind of things actually, right? Polymer. Okay, those things can be used at very high speed, right? And to avoid mechanical losses, it will be suspended. It will not be attached to the bearing and other things. It will be suspended in the like a magnetic levitation, right? So it will be running at very high speed, and it is a vacuum, and there is no friction, right? So when you run at very high speed, it can store more energy, and immediately when you need, it can supply, right? So that's the kind of flywheel mechanism we are going to have, or we are having in some places. Okay, right. So inertia constants for different machines are listed here: thermal, hydraulic, right? And it is you can understand per MVA. If it is 1000 MVA per MVA. The issue or challenge which I am talking about. See, when there's a frequency event, what is the frequency event? Loss of generating unit, or addition of big load. So what will happen? Immediately the frequency start to go down, right? Go low. Okay. So see, there are two cases considered here. If only SG synchronous generator, see you can look at the rate of change, or you can say the lowest frequency which you are attaining or which you are reaching during the contingency is this one. This is called frequency nadir, right? So that is somewhat less. When you don't have conventional synchronous generator, and also you don't have any inertia support, then the rate of change of frequency you can see is deeply decreasing. Also, it is going to the somewhat lower than the normal system, right? It is coming down, and of course once it is going to the value or some value, then the primary and secondary frequency control will come into picture, and it will start to improve the system frequency, right? Like this. Okay, of course, this is the time you are supposed to manage. Okay, right. Now, See, we are discussing about the inertia. That is, absolutely no doubt, it's a very big problem. Okay. The second one is this, California duck curve, right? What is it? This is actually a load curve, right? They are talking about, the load, or you can say the generation. You can take anything. So from 12 a.m. to 12, midnight, right? So it means midnight to this midnight. Okay, right. See, night time, the load is somewhere around 20,000 to 19,000 megawatt, and from 6 a.m. onwards, the California state or the region is having more and more rooftop solar PV. They are recently added up to the very high extent, and it started from 2013, and you can see the decreasing of demand, right? Or the decreasing of required load. By 2020, it is reached somewhere around 12,000 megawatt, but it was, 2012 or 13, it was around 19,000 megawatt, even more, right? Okay, so somewhere around 8,000 megawatt rooftop solar PV is contributing, right? Okay, so at the mid of the day, that is somewhere around 11 to 2 p.m., right? You can see the generation from the solar PV is very good. So you have, very less demand, or you can say less demand, right? And after that, the beauty is, after the evening time, like somewhere around 4 or 5 o'clock, the generation from the solar PV is coming down. So the demand from the conventional source or from the other state sources are getting increased, right? And it is reaching even 26,000 during, somewhere around 7 to 9 p.m., right? Now the question is, which kind of spinning reserve or which kind of source can handle this much deep or this much RAM? That's the big question mark, right? 13,000 megawatt change we are experiencing within 4 to 5 hours. That too, if you see this side, it is somewhere around 6 to 8,000 megawatt within very short time, right? Somewhere around 5:30 to 6:30. So 5:30 to 6:30 itself, or 5 to 7 itself, you are experiencing this much change. So how are we going to handle, right? So it's a big question actually. During the daytime, all the conventional sources, let it be natural gas based, because we are talking about California. So let it be natural gas, or the other conventional, can be nuclear, can be thermal, it can be any other thing, conventional, right? Not renewable based. So it is running at low or light load, and after 5:30 or 5 o'clock, it has to pick up, and that too within an hour, it has to pick up 8 to 10,000 megawatt, right? It is very difficult for the olden power plants. If all you are trying to do, you have to sacrifice the efficiency, the running cost, everything will be exceeding the the expected, or the allowed limit, right? So all those issues must be handled by the system operator by having a suitable energy storage, or you must be knowing that if at all I'm having a natural gas based generation, it will take very less time to come to the steady state. It means even if it is a 100 megawatt plant, natural gas based plant, the 100 megawatt will be reached within few minutes, right? Let us say within 5 minutes it will reach its full full power, right? But not all the sources, okay, right? So unfortunately in India we don't have much of natural gas based power generation, right? Still we are relying on the mostly thermal, around 60%, and hydro is very less, like 5 to 7 or somewhere around that, and nuclear, right? We are trying to reach, or we are in double digit figure, okay? So that should take care, right? It is not fair to ask the thermal power plant at very low load factor. You must be, you can understand that even if it's a generator, right? You can very easily say, right? See, let us say this is the efficiency and this is P out, right? What will happen normally? The efficiency curve will be like this. Most of the cases, right? Most of the cases, the peak power, or not peak power, peak efficiency, the maximum efficiency, somewhere around 70 to 80, or in some cases 85% of its maximum output, right, or rated output. Okay, so if you are forcing the a conventional thermal power plant to operate. See, this I am talking about only generator. Talking about the entire thermal power plant. You know, the entire thermal power plant, even if it is super thermal power plant, it will be around 35, little extra, little above the 35%, right? For most of the thermal power plant. So you can just imagine if the thermal power plants are asked to operate somewhere around 20%, 30% load of its maximum, power, you can understand what will be the efficiency of the thermal power plant overall, right? It will not be even 15%. It will be still less than the 15%, right? So it's all the hidden stories behind the conventional, or this is because of your renewables, right? So because of the government is telling that we have to evacuate maximum available power. We should not curtail. We should not spill out the wind, or we should not spill out the solar when it is available, when it is shining. But with the cost of all these things, right? With the cost of, when you do, or when you are operating the thermal power plant at somewhere around 20 to 30% load, it will go only, see, I'm telling you at the higher side, it will not be even, 15%. It will be still less than that. So you are, sacrificing lot, right? Okay, next. See, what is the curve you have explained? It is, the first time the researchers climbed from the California state load curve only. So that's why it is called California death curve. And this is what I explained, how the demand is increased during the evening time, right? And how are we going to meet, and different solutions for that was discussed in the literature. Okay. Anyway, since I was talking about California, you may be thinking that no, it is not to India. You can see this. This is measured by me. I'm a certified energy auditor by government of covering most of the northern Tamil Nadu region. Okay, right. So it was monitored or measured 22/8/2019, last year, right? And this is actually one of the agro plant, right? It is actually a milk processing industry, and there they have they are having 2 megawatt of solar rooftop PV, and their total demand is somewhere around 3.5 MVA, and out of which they are having 2 megawatt, right, of solar PV. And in one day, you can see somewhere around 6 a.m. it is starting, and it is going like this, right? See how badly it is changing. The first 3 are individual phase output power of one particular solar unit. See, they have 3 or 4 unit like this. I told you it is 2 megawatt, and we have taken from one unit, right? See, the maximum power is somewhere around 700 kilowatt altogether, 3 phase, right? But see here, it is varying between 700 kilowatt to 250, right? It is changing like this. The black is average, and red is maximum, and green is minimum, right? And you can see very well the black is average, and see it is varying like this. It is the one day, the second day is like this, third day is like this. See, in none of the day, as in most of the cases, our researchers, whether we are our students or our teachers, whoever it is, we used to take something like this, right? In a very safer way. In the morning it is 0, evening also it is 0, it is slowly rising and reaching here. But none of us are, considering like this. I hope you can understand, right? We normally used to take the solar PV curve like this. But in real scenario, this is the, solar power generation. So you can understand, right? So how much lagging we are, right? So this is one. So you can understand how other thing. Even in daytime, so-called from 11 to 1 is a peak generation period of solar PV. It is generating like this. It is highly random, highly varying. Right? So you can understand how difficult, for the grid operator to manage this kind of generation and the overall load demand, right? And the same thing we have expanded for one, particular hour. It is somewhere around, see here, 12:15 to 13:58. So somewhere around 1.5 hours. So within 1.5 hours, you just see here. Of course, this is the total power. So it is reaching its somewhere around 550 or 560 kilowatt. And suddenly it is coming to, around 180 kilowatt. It is varying like this only. See here, how badly it is varying, right? See, the black is actually active power, red is power factor, and, the blue is reactive power. See, this is reactive power. I think you can understand. So this is unity power. See here, it is 1.15 to 0.85. See, the good thing about the solar plants are it will always operate at 0.99 or 1 power factor. See, that's okay, very good. And also it will not extract or it will not take much of reactive power. Sometimes it will supply or very less reactive power will be taken by the PV plant. And this is actually the active power. So you can see how badly the active power is varying, right? And the next thing, this is another very important issue. This is taken at VIT. Of course, we also have 2 megawatt of solar plant in our rooftop. See, you can see 22 October 2020 and 229. See, it means we have monitored for one complete week, right, with the Fluke power quality analyzer. See, it is giving like this. What is this first of all? This is actually a harmonics, right? TSD, total harmonic distortion. You can see this is, total harmonic distortion. Okay, right. See, the black is TSD and red is, the fifth and other, fifth and seventh, everything. See, this particular day, it means 25th October, right? We experienced a characteristic something like this, right? See, 25th October, our TSD, total harmonic distortion, was somewhere around 80%. And it is not, same in all the days, other days also. In 24th October, you can see it is nearly 40%. Okay. What is this? Why it is so? Being an academic institute, university, you may think that, sir, you are telling lie, right? How can the TSD will be like this? 40%, 70%, I am not telling lie. See, I told you we have a 2 megawatt of solar plant. The beauty of solar plant is, irrespective of the load, it will generate always a good sinusoidal waveform voltage and good sinusoidal current. And of course, a unity power factor. So, in my university, of course, it is same for almost majority of the academic institutes. We almost replace every one of our lights into LED based. That is one thing. The second culprit, we have a lot of lifts because we have high-rise buildings. We have lift. All those lifts are VFD, variable frequency drives based lift, and most of the computer labs are connected with the front end UPS and then front end rectifier based UPS. Those are 6 pulse rectifiers. Okay, right. In academic institute we used to have very rarely the active front end based UPS. Mostly it is uncontrolled 6 pulse rectifier. I hope you must be able to understand. See, most of the cases, because being an academic institute, we are not much worried about the harmonics and other thing. So what we used to have? We used to have 6 pulse, conventional 6 pulse rectifier. That's it. So if it is 6 pulse rectifier of 300 kilowatt, 500 kilowatt, 700 kilowatt, something like that, then you will produce high, huge harmonics. That is what this, right? So this is night time. Night time, you see, TSD is not great, or TSD is not very high. It is somewhere around 10%. But during daytime, since 2 megawatt solar plant is producing a good sinusoidal current and voltage with the in phase, so the entire non-linearity and reactive power required. Of course, for reactive power we have the APFC or power factor cascade capacitors, but the harmonic, we don't have any harmonic filter. We don't have either passive harmonic filter double tune or active harmonic filter or active power filter, right? So passive, we don't have anything. So the entire harmonics required for the non-linear loads, let us say LED or variable frequency drive or UPS of front end converter of UPS and many like this, right? Almost all these are drawing highly non-linear current. So because of that, our TSD is something like this, right? If I give this to EB, then they will kick us, right? Because we are polluting, very much to the grid. Okay, right? So these are all the other issues. We are very happy that we are generating 2 megawatt of solar PV, but in the other side of the story, we are doing like this. We are polluting the grid to the very low extent, or very bad extent, right? So that's what this, right? So if at all you are planning for this kind of renewable, you must be taking care of all your harmonics which are generated by your load, right? Otherwise, this is what will happen. The customer who is very close to you will be badly affected. by this kind of waveforms or this kind of distortion. Okay. The next thing. See, we have discussed, right, when you have a more and more renewable penetration, you should take care of the inertia. At least you must generate virtual inertia from your power converter, and you must, take care of the ramp, high ramp up or ramp down during the day and night time. So everything, right? Above all, right, if at all you are going for a renewable power, right, you must have the forecasting, right? So that involves generation and transmission planning, right? It's for grid operator as well as an individual, individual, right, of consumer also. Okay. So generation and transmission planning, you must do it. See, very soon or, within very short time, we all are going to face, the EB, electricity board is going to ask, you schedule your, generation as well as load. It means you have to commit to the EB, yes, during 8 to 9 a.m. I will, take this much power. During 11 to 2 p.m., it means the hot summer, if it is, then I may need this much power. I have to commit or I have to schedule and give it to the EB at least 1 day ahead or, week ahead. It depends on the, the system operator. So if that is the case, you must forecast your load as well as your generation, right? So when only if you do all those things, then you can have a planning. See, the load dispatch center, regional load dispatch center, let it be, or in a very catchy word, system operator, a grid operator, system operator, or any DSO, distribution system operator, whoever it is, he needs some kind of figures, some kind of statistics in front of him. Only then he can plan. Yes, tomorrow I may need this much extra power. Then I can go for bidding to the nearby state or to the private power player. So all those things require some data, right? So that is why, so forecasting is required for load as well as generation, right? So only then you can have a flexibility, right? And once if you have flexibility, you can have reliable power, right? Right. So medium to long term planning, yes, it can be a few hours ahead or 1 day ahead or few days ahead or yearly, it can be anything, right? And day ahead planning, intraday, then balancing. So as a whole, when you have more and more renewables and highly varying load and of course some very few percentage of conventional generators, right? Then you must have a mechanism to match instantly the generation and load, right? That can be done in a different way. You must be some of you at least, right? Some of you must be knowing the demand side management, right? But what we are doing now, presently, the electricity board or the district or the distribution centers, a few districts will be combined as one region within a state, right? So from there you may get a call, sir, please, so and so time, and we have some lack of generation, please switch off your load. Or they may announce, see, during this time we may not able to give the power to you, something like that. This is called load setting. Similarly, in future they may ask some people, right, sir, see, you have this much of generation, being a private power player, you are supposed to, or you need to give this much excess power during this hour, something like that, right? So all these things, the grid operator or the distribution system operator should exercise to have a reliable and safe, power, right? Then I was telling about demand side management categories. So how can I do the, in ground reality, what is happening and how it can be done? See, let us say this is the kind of load. So what I can do, I can set the peak, right, to somewhere here and here. For example, if I have if I'm running a textile mill, big, textile or spinning industries, what I can do, I can run my compressors to compress the air and keep it in a vacuum, or you can you can say storage, right? I can compress the air and store, right, during the off peak hour, so that I will assure like I will not run my big compressors during the peak period. This is one thing. If it is refrigeration mechanism, I will freeze, or you can say I will chill the water and I will make it as ice and will keep it for the requirement as per the process, right? I can do that. So if I do that, maybe my chiller plant or my the refrigeration unit will have less power consumption during this time. So I can store it by freezing something, right, during these periods. That I can do. So this is called load shifting, right? Or I can just rearrange my process flow in such a way I can use more power during the off peak periods, and during peak hours I can reduce the power consumption. And value filling, this also I can do it, right, by adjusting these two sides. Okay. Or you can just compress it, or you can push the peak saving, right? That also you can do it. Or in any of the way this can be improved, or that, right? So that you can do it by adjusting the it's like a spring, right? See, for example, my first project for Tisco was something like, during night time the people said like the sodium vapor lamp is consuming a lot of power. Even when there is no movement, it is consuming more power. You must be knowing that sodium vapor lamps are negative resistance coefficient, or you can say once the sodium is getting vaporized, then the resistance will be something like a non-linear change it will experience. So even if you reduce some amount of voltage, there will not be much change in the illumination, right? So what we did, we adjusted the transformer settings, tap settings, right, in such a way. During night time, at least I used to reduce 30% of the voltage, but nothing was happened actually. Even we measured the illumination from the sodium vapor lamp, even after reduction of 30% of voltage, nothing was happened, right? This also we have experienced. So in this way, we have reduced some power, power consumption, or we have saved some power consumption. It is not only sodium vapor lamp. I just told you one example. It is for all, right? See, nowadays LEDs, it's all big. In some cases it is power drive, or in some cases just a converter, and that will be feeding to the LED driver. There is a driver. Okay, so the driver will be the driver will ride through even for 30-35% of voltage. Ride through in the sense, even when the voltage is not up to the 100% level, even if it is 80 or 75%, it will operate in a very safe way without losing its the performance and other thing, right? So in that way also you can reduce the transformer tap settings during night time, and you can save the power. So all those things can be done, right, with this. Okay, the next is, see, one is demand side management, right? In that way also I can compromise, or I can say I can manage the load and demand, right? It means generation and demand, or generation and load. Okay, the other way, right, it means many of the developed countries, right, yeah, which those who are very rich in the electricity, right, they are having this kind of things, right? Energy storage technologies. Okay, see, out of many techniques shown and many methods shown, some are highly already grown and standardized, and it is available in the market as a standard product, right? And some are in laboratory level. It is still needs some time to mature, so that once the technology is matured, then because of the mass production, the cost can come down, right? Like solar PV. Okay, right. So the different types of energy storage technologies are chemical, electrical, mechanical, thermal, and electrochemical, right? And under each category, I have just listed out some energy storage methods, or you can say classifications. Okay, right. So I told you in energy storage also there are two kinds, I can say, because I'm interested very much in energy storage technologies for grids ancillary services, or you can say grid support services. Okay, most of my researchers are in that area only. So the energy storages system or energy storage technologies can be classified into two. Some energy storage systems or energy storage technology, or devices can help for a short time, and if you see the ramp, it means how fast it can generate from very low, or it can supply, it can charge or discharge from low level to high power. For example, if the rating of the energy storage is, let us say, 500 kilowatt, right? The ramp is something like how fast it can reach from 0 to 500 kilowatt. Similarly, how fast it can reach from 500 kilowatt to 0, right? Or in any intermediate stage. So how fast it can change, it can accommodate the need, right? It can be charging or discharging, right? That's actually ramping. So some devices or some technology, for example, flywheel, right? Capacitors, supercapacitors, of course, right? Electric double layer capacitors are supercapacitors. Then supermagnetic energy storage. See, SMES, capacitors, flywheels. All these three are very fast. See, it can charge at very rapidly. Also, it can discharge. If you want very high rated power in a very short period, yes, you can get it from capacitor and supermagnetic energy storage system or flywheel. Similarly, the other sources, right? For example, if you take pumped hydro power plant, right? Pumped hydro or pumped things like in Tamil Nadu we have Kanambare, right? We have a very good example for pumped hydro power plant. See, during the off-peak period, the induction motor or pump, it is actually induction generator. The pump will pump the water from lower reservoir to upper reservoir. That is lower Aliar Dam to higher, upper Aliar Dam. That's the name of the Kadambare, power plant. Upper Aliar and lower Aliar, right? And you can do pumping when it is off-peak period. When it is peak period, of course, the base power plant, it means the thermal power plants will take care of a constant load. The sudden change, the transient power requirements are taken care by the, the pumped hydro. So during that time, you can just run and discharge the water to the, from upper to lower reservoir. Then you will generate power and give the backup, right? So, but it takes some time, right? So pumped hydro is not very high dynamic. It takes some few seconds, 2 minutes, right? Similarly for all, right? So compressed air energy storage system, right? Or hydrogen based. It means hydrogen fuel should be burned, and maybe you can use a fuel cell, and the fuel cell will take the hydrogen and will generate the power. You must be understanding, or you must know that fuel cell is not very fast actually. It cannot be loaded, very abruptly. It takes some time, right? If you try to load, then it will create a lot of issues. Okay. Similarly, batteries. Though batteries are fast, but it is not as fast or as early as this flywheel or capacitor or SMEs, right? This is very fast when compared to batteries, right? In batteries also, see, India is doing very good in NAS, sodium sulfur battery, right? Of course, in India also, in some of the places in Bangalore, I know one case, and in North also I have one or two literature. See, they are using flow batteries. Flow batteries are something like, see, this is also a battery. There will be two, electrodes, and there will be a, dielectric, or you can say, what is the electrolyzer, right? Something like that. So there will be a, two tank in, either sides of the battery cell, and from one side the charged, electrolyte will be passed through the cells, the electrodes. When it is charged and it is going through, the active, energy or the charging will be coming through the battery and battery cells, and you will get the power. And after releasing the energy, it will go and store in the other tank, right? And once it is fully discharged, then you can charge by pumping the water from this side to the other side. Of course, you have to send the electricity to the electrode, right? So that it will take the charge and will go and store it, right? The biggest advantage of flow batteries, it can be modular. You can add any amount. It means if at all you want to have a high energy density, you can go for flow batteries, right? Okay, so this is what I was talking. See, there are two different terms, energy density and power density. High power density are required for transient responses, like high power density devices are flywheel, capacitor and SMEs. And high energy density devices are like, the pumped hydro, right? Even batteries and all these, thermal storage things, right? So, in thermal, of course, you can increase power density by adding more and more cells in series and parallel. And by, having more energy density, like, flow battery, you can have bigger tanks so that you can have more energy stored, right? Okay. So, the day, this day belongs to lithium ion, because, most of the EVs, lithium phosphate, lithium ion and lithium polymer, many, right? So, those are very costly. The availability of lithium, right, is a big question mark. So that's why it is costly. Otherwise, it will not be much costlier, right? Okay. So of course, lead acid is slowly, going out of the market, and other things are, right. Nickel cadmium for small level, smaller power backup. Nickel metal hydride is also for smaller range. But Na is lithium ion, or for is a very promising candidate for the grid level energy storage, right? When you compare the cell voltage between lead acid and lithium ion lead acid is just somewhere around 1.5, something like that. From one cell you will get maximum of 1.6 or 1.7 voltage. That's it, right? 1.5. But lithium ion, even it can reach from 3.7 to 4.3 voltage per cell. I'm talking, right? So obviously the energy density, the number of cells handled, everything, right? Cell balancing, everything is easier in lithium ion, right? Also in NAS batteries, right? Okay. Then see, this particular slide is giving insight, like an idea, brief idea. What are the different ways the energy storage can help, to the system, right? See, if it is a generation, right, the energy storage will play very big role in black start. For example, in a microgrid, conventional microgrid, if you have different sources, right, you cannot start some sources. For example, mostly the wind or solar. You need the grid, right? So only if you have a grid, then base log loop will find out the frequency and it will produce the frequency, voltage and current at that frequency, and it will be synchronized, right? So the battery, the energy storage only can start the inverter first because the energy is available, and it can dictate the frequency and voltage to the rest of the element, right? That's called black start. It means when it is blackout, out of many sources, which source can start first and will give the frequency reference to the others. That's called black start, right? That is mostly battery, right? Battery based sources only can start first and will dictate the frequency to the other people, right? Other elements. Okay. So energy arbitrage, it can help in that way. Our support to conventional generation, yes, right? And renewables, yes, distributed generation flexibility. This is something like power smoothing, right? See, the solar power may be very very dynamic or highly dynamic. For example, if you take a solar PV, it is something like this, right? Something like this. I don't think I'm drawing this easy. It's a highly dynamic power I'm representing, right? But the grid operator, the load, may want something like this, right? The grid operator may expect you to give a power like this. So how to make this kind of change into a constant power? That is with the energy storage. Either you can use MPPT, but MPPT this can be brought to this point, but this cannot be taken to this point by using MPPT, right? So you must understand that. So if you have energy storage, yes, even if the generation is like this, highly varying, I can smooth the power. It means whenever there is extra power generation, you can store it to your battery, and when there very good, very good, but you may not need the power. So what you can do, if you have energy storage, you can just produce and store it, something like that. You can do it, right? In transmission also you can do primary frequency control, secondary frequency control, right? So all those things, investment definitely. See, this is something like the government is finding a lot of difficulty to establish a good transmission line, to take the extra power states, extra generation power states to the the power, the states where you have less in generation. So the government is finding a lot of difficulty. So what you can do, when you allow this kind of distributed generation and energy storage, for time being you need not invest more, and you can have the backup and the other contingency issues, everything can be solved with the energy storage, right? Then distribution, yes, capacity support, dynamic local voltage control, conditions in grid support. See, grid support, that's what I told you. I am working on grid ancillary services from the energy storage. This is something like, see, I will always deduct or find the frequency. When the frequency goes low, what I will do, being an energy storage man, I will just start to supply so that I can regulate the frequency. That is one thing. Similarly, when the frequency is going up, what I will do, I will suck the power. It means I will take the power so that the the balancing between generation and load can happen, right? So all those things I can do it, right? And also, see, suddenly if generating station goes away, goes out, right? Cut. then what I can do, I can supply the power till the next generation comes into picture, right? So all those things I can do it. That is what actually this. Then end user peak saving, yes. See, in many restructured or what is it? Time based tariff. In some of the countries they are following this, or the frequency based tariff, right? So what you can do if you have energy storage, good amount of energy storage. When the price is high, it means when the frequency is low, it means load is more than the generation. So it is well known that when the frequency is low, the price of the electricity is high. So you need not take the power from the grid. That time you can use your battery, right? Or in the best case, even you can supply to the grid. You can sell the power at a higher cost than you purchased price, right? That is one thing. So that's what actually the time of use energy cost management, and power quality of course can be improved, right? Inertia and other support can be given from the energy storage, right? So this is what I was talking. Some energy storage will come for hours and days, and even it can store high amount of energy. So it is these things are called high energy density devices, right? And super capacitors, super magnetic energy storage system, flywheels, right? All those things will support for very less time, very short time, and its rating is depending on the technology, maturity of the technology, right? Even super magnetic energy storage is available, as per this few tens of megawatt, right? Of course, it can support for very short time, right? Lead acid, you can see, NAS, I told you, right? See, India can do very much, great things in NAS because the availability of sodium sulfur, right? We need not depend on lithium and other things from the, what is it, nearby countries, right? We need not, what is it, pay many things, right? Pay much to the lithium, right? So this is available everywhere, okay. All right, so all those, you can just see, and vanadium redox flow battery, polysulfide, there's everything, all these zinc chloride, zinc gas, zinc bromium, all these things are flow batteries. And there are a lot of good research is going on in flow batteries, right? Of course, it's not very what is it, very sharp or very rapid growing field, but there are good research going on, and there are many vendors also start to supply. Of course, the VRB, VRB is a very mature technology. Of course, in some extent, PSB also. So they start to supply VRB flow batteries, right? In Bangalore, in one area, I know 200 kilowatt hour of flow batteries used. It's a small system campus, right? For that, they have installed flow battery. See, the life of the flow battery is, very good. There is no, number of cycles, nothing. See, you just pump the, electricity from here to the other side, and once it is charged, we can allow this, the electricity to the other side. So there is no limitation in number of cycles, right? The, nearly 20 years this flow battery will support, right? With a very minor maintenance. But whereas, if you take lithium ion or other things, it can come for like 5,000, 6,000 cycles or 3 to 5 years. And if you take a lead acid battery, it will come only for less than 3,000 cycles and 3 years, right? Whichever is, earlier. So all those things are there, it depends on the cost and number of cycles, life, everything, okay? What is it? A decent comparison is shown here. Pumped hydro storage, right? Just a minute. See, pumped hydro storage, the available size is 100 to 5,000 megawatt, right? Discharge time, there is no limit as long as you are storing the water. Of course, due to the environmental conditions, it may evaporate to some extent, right? But it's not much. And power density, see here, it is very less, right? It's a very old energy storage technology, but still, we are using because it's highly reliable and very big, okay? Because of that, it is 0.1 to 0.2 only, right? So watt per, the weight and other things, right? Power density is very less. Similarly, energy density, right? Watt hour per liter, that is also very less for pumped hydro storage, right? Then response time. See, it is not as fast as your flywheel or super capacitor. It is little slow only. You have to start the pump or generator, then only it will start to inject the power, right? It takes some time to settle to the particular speed, steady state speed, and it will start to inject, right, the power. Compressed air energy storage is also in abroad countries, in developed countries, they are having this kind of thing, right? The windmills, when the power is not required, it means when there is excess power, the windmill can be used to compress the air and store it in the underground cavern. And when the power is required more, then the compressed air can be sent to the generator or turbine. Then you can have a fuel mix and you can generate the power, right? So this is also having a discharge time of 1 to 24 hours, even more than that, right? And the power density is not good. And this is also like your PHSS, pumped hydro storage, and the energy density is somewhat good, right? Yes, when compared to PHS, it is somewhat good, and response time also minimum, right? And flywheel energy storage system, right? Power rating is very less. You cannot have very high, rating, and it is discharging time is seconds to hours, and power density is very good, and energy density is reasonably good, and response time is less than second. As and when you need a power, it can supply, right? Because it's a rotating mass. Just you are converting that motor to generator. That's it. It means when you give the electricity, then it will act as a motor and rotate the big flywheel. When it is not, then it will start to generate because of the inertia, kinetic energy, right? And lead acid is given like this, nickel cadmium, lithium ion. You can see here, right? See, the power density is very good in lithium ion. Yeah, Na is also is good, not very bad. And all those, right? VRB, zinc bromide, then fuel cell, supercapacitor, right? Supermagnetic SMEs. So all those things you can just see it. SMEs also is, there are good research is going on, in cryogenic based field or environment. You can keep the coil of high current density and you can send more current, very high current. Of course, of a DC, right? You must have AC to DC, then that very high quantity of current is flowing through the coil, which is kept in a cryogenic, very low temperature vessel or closed medium. Then it will store half Li square, right? Energy stored in the inductor is half Li square. Then when you need, then the current flow will be taken to the DC to AC converter, and you can inject the power to the AC or in DC level itself, right? Then again, some more, in different comparison. So what is the efficiency of different type of energy storage, and what is the capital cost involved? Of course, see, this slide is prepared based on the 2015 scenario. See, there will be reduction in all these things, right? Improvement in efficiency, right? Everything. Okay. So, of course, when I was, exploring, I was not able to get 2020 or 19 or 18 data. So, since I got readily, so I just put it here. Okay. Efficiency, you can see, PHS is good, and lithium ion you can see here, and all these things, right? You just see here, right? Super capacitor is like a capacitor, so you will have a very good efficiency, and there's no limitation in number of cycles. Okay, so you can just see here, right? See, though it is given 104 to 105, but it will be much more than that, right? Okay, and again, another different parameters are taken and compared for different energy storage devices. We can just go through after some time. Okay. See, we have discussed how I can do demand side management so that I can overcome the variability of the renewable energy sources. And the next thing is, if I have an energy storage, what are the different types of energy storage and how I can take care of the variability of energy storage. Yes, that is also one. And beyond that, by just incorporating some good control also, I can do something on the variability. Different things are discussed here, right? Soft start, reactive power sharing, decentralized power control, mode of flexibility, fault tolerance is very important, right? It means right through, right? It's like a low voltage right through, fault right through, high voltage right through, right? Many things, right? And then islanding direction, prognosis, right? So it means self-healing, right? All those things can be, can be incorporated in the inverters, smart inverters. Okay. So next thing is, how through inverter of solar PV or wind, I can bring the inertia. It means I can imitate, right? I can convert my solar PV inverter, like a synchronous generator character, right? That's what this. So you can just, keep measure the grid frequency, and whenever there's, something wrong with the grid frequency, and that can be sent or passed through the damping coefficient, and the power set will be adjusted accordingly, and finally you will get a PWM generation to the inverter. So it will generate more power if the frequency is less, or if the frequency is more, it means higher omega G, will reduce the power generation. Accordingly, the PWM pulse will be generated. And not only that one, based on the requirement of reactive power also, I can adjust the inverter, right? So you can just do all the things, then reactive power I can set whatever the value I want, right? So if at all you are doing low voltage right through, in majority of the cases you should generate reactive power, right, to take care of the voltage related issues, low voltage related issues, right? So that's why reactive power compensation based voltage restoration, right? So that also you can do it, right? This is actually emulated inertia control technique, right? You can emulate the synchronous generator character with PV inverter. That's what actually this thing, right? This is the another things, we told fault tolerance right through, right? So this is one such thing, that is low voltage right through. See, the wind turbines or wind generation techniques which are working or which are functioning from before 2000 or before 1990, right, like 20 years back, 30 years back itself, we have some windmills. Those windmills, the setting is something like when the voltage exceeds upper or lower threshold or upper or lower limit, what will happen immediately, the windmill will just isolate itself. It will just stop generating the power and it will come to the off position. So you just imagine, see, let us say because of the overload, right? What is happening because of the overload? The voltage is coming down. By detecting the under voltage, the windmills are slowly cutting out or isolating island, going to island one by one. So what will happen? It will be a cascade failure. Already there is a overload, that's why the voltage is low. And if windmills are stop to generate power because of the low voltage, then it is very bad. So we must incorporate right through. Even when the voltage is low, your wind generators must be in a position to generate active power, right? And when the voltage is low, your wind generator should supply some reactive power. Your wind generator should supply some reactive power so that the reactive power will help for voltage voltage improvement, right? Just a minute. Just 1 minute. I'm sorry for the interruption. So, the LVRT is also a very important requirement for the recent, the grid. The grid is more smarter, then your devices also should be very smart enough to handle right through the changes in the grid, right? And so this this is a one technique, a simple technique to handle the right through. You can go through it. See, based on the terminal voltage, or you can say point of common coupling voltage, the amount of reactive power supplied to the grid be decided, right? See, when the change in voltage to the near normal voltage, if it is 50%, you can see from the characteristic, when the change, it means when there's a sag under voltage and if the voltage is only 50% of the actual voltage, then the entire rating of your converter must be used to generate the reactive power. I repeat, if the system voltage is only 50%, it means 0.5 per unit, let us say, then the entire rating of your power converter, renewable source power converter, must be used to generate the reactive power and inject. That's the meaning of this, right? And similarly, how the control can be incorporated. See, there are two modes: normal operating mode and LVRT mode, or FRT mode, or HVRT mode, right? Then all those things are taken care. So that's what you are seeing here. Okay, and this is again based on the the residual voltage, the control should be operating, right? So that it will take care of the voltage change, right? At the outside, when you add more and more renewable sources, you must have a lot of flexible generators, right? It means maintaining sufficient capacity of the system for planning reserve. When there's a contingency, you must be in a position to supply from the reserve, right? And how much you are investing and what is the cost behind that, all those things should be worked out, right? You must be knowing that in future you are going to have, like Airtel, Vodafone, something like that. You also have 3 or 4 choices. I need 100% reliable power of very good quality. Yes, you have to pay for 7 rupees per unit or 8 rupees per unit. Or some people can say, no, I don't want 100% reliable. I may need only 95%. And power quality also, even something less, I can adjust. Then you have to pay 6 rupees per unit. And some people will say, no, I'm very poor. I need the power. See, as and when it is available. Or I'm not worried about the reliability, or I'm not worried about this power quality. Then you may need to pay only 3 rupees per unit. Something like that, I'm just telling you, right? So, because if you have more and more spinning reserve or flexible generation, the cost will increase ultimately. So how are you going to overcome that, right? And the dispatchable renewables. See, at present we are okay, we are managing. But if more and more electric vehicles are coming, what will happen? See, if every electric vehicles or charging stations are planted here and there, and that too fast or rapid charging, so definitely it will spoil the voltage regulation, frequency regulation, right? And it may increase the losses right? So it will be uneven power flow. It is very difficult to predict by the grid operator or distribution system operator. So at that time, you can, if you have a green sources based renewable that is renewable based charging stations, only by having energy storage, you can say yes, I have a dispatchable renewables. And also, we are we are talking about issues of electricity in one side, but the other side, we also can take energy from the vehicle, that is vehicle to grid, right? By having a aggregated EV batteries, the charging station can plan or can do capacity farming, right? That something like that can be done to help to the grid or to do the energy transaction, right? The EV owners can earn some money during with this. All those things can be done, right? And demand response, we have discussed interruptible load. It means flexible load. See, in a simple way, V squared by R is the power. By adjusting voltage, I can decrease or increase the power consumption of load. I hope you can understand, right? V squared by R is the power. By adjusting the voltage of the load, I can decrease or increase the power consumption of the load. So that's also I can do it, right? That's called different kind of demand response. And controlled charging of electric vehicles, yes, we have discussed. And storage is very important. And when it is produced mass, then the storage cost also will come down, right? And if you do that, then the curtailment, whether it is a load curtailment or a source curtailment, a shedding, right? Those things can be avoided. And transmission will be made pakka. You have a very good hereafter it is not fair to invest more on building or having very good transmission infrastructure. Instead, you can invest something in the green or distributed generation, so that we can strengthen the grid or power system still better without doing much in the transmission infrastructure. So that's also can be done, right? And all other things like advanced metering instrument. So everything is required to balance, to stable the grid, right? So we have discussed all these things, right? And reflect market status. Yes, the economy also will come into picture when you have more and more penetration of renewables, right? So this is also almost we have discussed, right? Okay. See, I'm open for the question, right? If at all you have questions, yes, you can we can discuss. Yes, please. So no one is with me or what? Hello, gentlemen and ladies.
Thank you, sir, for the session. So I request the participants, you can ask the queries related to the session, or else you can type your queries in the chat box.
Before starting that, we have established a smart grid of 100 kVA. I just interested to show this the participant. Yeah, please hold on. Has evolved from the liberal funding that's
Challenges in renewable source integration. ఎవరు క్వశ్చన్
YouTube live నడుస్తారా వాళ్ళు వెళ్తాం YouTube live వాళ్ళు
వీటిలో పెట్టండి వీటిలో ఉంది కదా.
Yeah, see, I've just shown the smart grid laboratory which we have developed in our School of Electrical Engineering. That is having 1 kVA fuel cell, 10 kVA wind emulator and solar PV emulator, then 5 kWh of lithium-ion battery, and with 160 farad of smart super capacitors. Then the grid emulator. We have 3 grid emulator, 100 kVA, and 2 other things are 11 kVA each. So I can, of course, we have a low polarity. It's a high-end digital, real-time digital simulation infrastructure from low polarity. So we can realize power hardware and loop system. This is something like a controlled environment you can build. The device under test can be anything. The converter you are building, or renewable energy sources you are making. So those things can be just connect, and you can check your developed topology or control algorithm or control technique with our controlled environment. So this will help you, if at all when there is a over voltage, under voltage, frequency change, how your developed inverter or converter can interact with a safe, protected manner to your grid. Whether your control system or control technique or control algorithm developed is robust, how robust it is, right? So all those things can be tested with our power hardware and loop environment, right? So this is funded by Department of Science and Technology under a FIST category. Then VIT spent 1 crore 15 lakhs, and they also given 1.15 crore. So we have established this one. Thank you. Now I'm open for the questions. Oh, you want me to read that chat box? Anyway, I will try.
Sir, sir, I'll be reading, sir.
Yeah, please, yes. I don't think there is a question, right? One guy have written nice lab. That's it. Okay. So see, my name and other contact details, you can get it from the the organizer. My area of research is hybrid energy storage system. It means 2 different response characteristics, like the high fast things, that is super capacitor and flywheel, then SMES, that how that will interact with the other side, high energy density device, battery, or any other kind of energy storage. So hybrid energy storage system and its role, or in how it can support to the grid for its ancillary services. That will be frequency regulation, voltage regulation, or peak saving, energy transaction, can be anything, right? That is one major area which I am working. Then the second is actually I'm also doing some work and guiding 1 or 2 students in virtual inertia. If the renewable converter power source is connected to the grid, then there's a frequency related issue. How, as a power converter, right, we can imitate the power converter or power source as a synchronous generator. You can convert your renewable sources into a synchronous generator, so that it will involve the frequency regulation. We can support by injecting more active power or absorbing some active power, right? Something like that. So in inertia also I'm working, and my other area is actually LVRT, FRT, right? How the different renewable sources can support in LVRT fault right through, right? See, when there's a fault, the entire fault current or fault power need not come from the main grid or the bigger generator size. If you are also contributing to the fault by supplying some fault current, right? You have to increase the fault current by supplying more fault current. What you can do, when the grid supplies less fault current, the voltage, right? The voltage drop in the line will be drastically reduced. Now, if it is operated in a coordinated manner, even during the fault, right? Of course, the sensors, other relays will detect and it will do the remedial action. But still, if you contribute some fault current, the recovery will be faster, right? That is also one of the area where I'm working. That's what actually right through, right? The fault right through, LVRT, FRT, all those things are in that one. Okay. And of course, energy management in microgrid, interconnected microgrids, transactive energy. Though I'm telling many things, but it's all related to battery energy storage system, right? Converter technology, inverter technology, only that much, right? And I'm a certified energy auditor by Government of India. I'm helping in energy saving, power quality monitoring, power quality audit. So in that way also I'm helping the nearby industries. Yes. So I think people are taking rest. It's fine. The time is like that. Dr. Sudhir.
Sir,
Yeah.
Can you please give us one more minute, sir? Actually, we are checking in YouTube also, sir.
Yeah, please. Yeah, please.
Sir.
Yes, sir. Yes, doctor. Please.
Actually, during the registration, we got two queries, sir.
Yeah, please. You can.
Can you read out, sir, those? So the first question is, sir, Mr. Suresh, he's asking during registration, he asked he wants to know which combination of renewable energy sources is the best for grid integration.
This is not actually a discrete answer, definitely, right? Nobody can give a accurate answer to this. See, combination, this is something like, people are talking about solar and wind, because, solar will be good during, morning 6 a.m. to 6 p.m. and wind will be picking up in the early morning as well as in the evening time. So when you connect together, whenever, see, during daytime, it means the, afternoon time, the wind will be somewhat less. But during night and evening time, this will be good. So when you connect, equal size, let us say, right, equal size of wind and solar, this is something like, a combination which will fit, with the lesser change. Otherwise, if you have only solar, you'll have a peak like this, right? And if you have only wind, right, during night time it will be somewhat good, but in the morning time it will come down, and when it is peak, it will not give the power, something like that, right? But when you combine, yes, it can behave in a proper way, right? And moreover, see, even if you have solar and wind, if you have energy storage, yes, you can smooth the power. It means only then you can claim your renewable sources as dispatchable, right? It means you should make a constant power, right?
Yes, sir.
See,
Yes.
it is, it will help or it will enable the grid operator or distribution system operator to plan properly. See, as per CEA, Central Electricity Authority, your forecasting or your scheduling can vary plus or minus 15%.
Okay.
As per CEA, National Institute of Wind Energy or National Institute of Solar Energy, those people and experts are telling that their predictions reached somewhere around single digit accuracy. It means they can predict with the error of less than 8%. So the prediction accuracy is 92%. So in one side, the Central Electricity Authority is telling that plus or minus 15% change you can have. For example, if you have scheduled or if you have committed 100 kilowatt, you
Yes,
can
sir.
have plus or minus 15 kilowatt up or down. It is allowed. You will not be penalized because of the change. But as per NIVE, National Institute of Energy and National Institute of Solar Energy, they are telling that they are able to forecast solar and wind to the level of 92% accuracy.
Okay.
So, anyway, that is okay. But beyond everything, if there's a sudden change because of unexpected, environmental change, then yeah, you need your, backup of energy storage or some other spinning.
Okay. Sir, one more query, sir. This is from Gautam, sir. Mr. Gautam, he is asking which area should be focused more in renewable grid integration?
No, Sudhir, your voice is not clear. Can you repeat the question?
Sir, Mr. Gautam, he during the registration he asked this question, sir. He is asking which area should be focused more in renewable source grid integration?
Okay. Yeah, this is very nice question. See, at the end of this meeting, I told you my working area. That is nothing but these are areas, are very hot, are very, it's all evergreen, like the grid ancillary services, right? Something like when you have a solar or any other renewable sources,
Yes.
how effectively you can do some grid support services with the help of course, energy, right? That is one area. And the effective control, that is ride through, low voltage ride, fault ride through, that is another area. See, you may have a very good control of active, reactive power, protection. You can of course make power quality, everything. But when there's a contingency, when there is under voltage, over voltage, then frequency regulation or frequency changes, how your inverter or inverter control should operate, right?
Yes, sir.
How robust is your control is based on during the contingency how your inverter is performing. Whether it is just sometimes when there's a considerable change, your inverter will not be educated or inverter will not be equipped with what to do during the contingency.
Yes.
Right?
Yes.
So that should not be the case. So you have to allow the inverter different power quality disturbances, and you should train. It means you should incorporate all those abnormal mode and functionality during that time. So that is also in another area, right? And moreover, how the energy storage system will help to smooth the power. Only then you can say your renewable source is dispatchable, capacity firming, right? Something like that. That's a very good area.
Okay. Participants, if you have any queries, please you can unmute yourself and you can speak with the sir.
Okay. See, if time permits or if you are coming for, PAT to attend any other programs, right?
Fine. Yes, sir.
You are, invited, or you are most welcome to my lab, Smart Grid Lab, and I'm very happy to take you, and I will explain what kind of work we are doing in our lab, right? So everything. So thank you, Sudhir, and your partners and participants. Thanks a lot. Right? I'm not sure how effective is my session, but anyway, right? If I am, just created an interest in something like, the LVRT, FRT, and other things, right? I will be very happy to, collaborate you in future. Okay. Thank you. Bye bye.
Thank you so much, sir.
Thank you. I think our Dr. Kumar has joined recently, right?
Sir, sir,
Yeah. Yes.
sir, we have one query in YouTube, sir.
Yeah. Please.
How can control over generation during periods of low demand in certain areas?
No, the question is not clear. Can you repeat?
How can control over generation during periods of low demand in certain areas?
Low demand or load demand?
Less demand, sir. Less demand.
Okay. See, it's MPPT. See, MPPT is not only for solar, but also for wind. See, when you try to change the voltage of the solar PV, by adjusting the duty ratio, then you can also change the power, right? So based on the power need, you can adjust your voltage, and so that current can be changed. Then you will get the required power. So with MPPT, you can reduce the power generation. MPPT is for maximum power transfer, but
yes,
the same can be used to adjust the voltage so that you can reduce the power even when the solar can be more, right? That can be done. This is same for wind also, right? By adjusting the electrical torque, by adjusting the the DQ or some other parameters, you can change the speed, right? So obviously you can change the power.
Yes.
Or storage, right? You generate whatever is available and store it, you can control.
Okay, sir.
That's also can be done. See, people will, most of the people will think that, that's the wind. And if you are not loading to the good extent, the windmill will start to run at very high speed. No, it will not happen, right? So, you need not worry.
Correct. Yes, sir.
Like generator, right? It will not happen.
Sir, I guess all the so they have cleared all the doubts whatever they have, sir. Sir, in future also we require your help, sir, for the next phase also. Thank you so much, sir, for spending your valuable time, sir.
Thank you, sir.
We are planning on smart grid, sir. Next phase in December 2nd week. So we require your help, sir.
Thank you.
On behalf of our management and our department committee members, I heartfully thank you for spending your valuable time with us and sharing valuable information to our participants. On behalf of participants, I assure you they will utilize this session for in their research and their future development. Sir. Thank you so much, sir. Thank you so much again, once again, sir.
Thank you. Bye-bye.
Bye, sir. Thank you.